In this video, we look at binomial probability examples. So a binomial experiment, the idea here is you have a set of trials where you're doing the same thing over and over again. And binomial implies two possible outcomes, either success or failure. Now you can have an experiment where there are more than two possible outcomes, but we kind of define these outcomes are success, these outcomes are failures. So that's where the term binomial comes. So you can think of n as the number of trials. So this is the experiment that I'm repeating over and over and again. I'm doing the same thing, trial after trial after trial. So n is the fixed number of trials. P is the probability of success on any given trial. So each time you do the experiment, there's a P chance that it will be a success. 1 minus P then, Q, would be the probability of a failure on a given trial. So if R is the number of successes in a fixed number of trials, we say R is a binomial random variable. And so here's the formula for the probability distribution function for a binomial. It looks a little messy. The nice thing is it works for any binomial experiment. All you need is n, the number of trials, and p, the probability of success, and then r, how many successes do you want in a fixed number of trials. So remember, factorials means you multiply down the integers. So 5 factorial is 5 times 4 times 3 times 2 times 1. 10 factorial is 10 times 9 times 8 all the way down to 1. And so this formula can sometimes simplify. Also note that the TI-83 and 84 calculators have the binomial probability function built in. There are also lots of calculators online which will calculate binomial probabilities. Additionally, your statistics textbook has an appendix with tables, and there are binomial probability tables, so you can look up these probabilities using the tables. So if we look at some examples, first let's take a simple example where we roll a die, and we're going to count the number of 5s. So if R is the number of 5s, that's what I'm calling a success. Anything else is a failure. So here note there's actually 6 possibilities, but I'm calling a 5 a success and anything else is a failure. So there's my 2 success or failures. So R is a binomial with n equals 10 because I'm going to do this 10 times. I'm going to roll the die 10 times. Every time I roll the die, there's a 1 in 6 chance I get a success, a 1 in 6 chance that I actually roll a 5. So if I asked what's the probability of 2 5s in 10 tosses, I roll a die 10 times, what's the likelihood I get exactly 2 5s? If I plug this into the formula, I'm simply plugging in n equals 10, r equals 2, and p equals 1/6. So if p is 1/6, that means q is 5/6. So if I plug all that in, I get 2907, or about a 29% chance I get 2 5s and 8 of something else. Now note that that factorial part does simplify. 10 factorial is 10 times 9 times 8 times 7, etc. 2 factorial is 2 times 1. 8 factorial is 876. So notice I have an 876 all the way down to 1 in the numerator and an 876 all the way down in the denominator. So those could cancel each other out, and I'm left with 10 times 9 over 2 times 1, or 90 over 2, which is 45. And what that represents is if I have 10 tosses of the die and I want exactly 2 of them to be 5s and the other 8 to be something else, there's 45 different arrangements of that, different ways I could arrange 2 successes in 10 trials. So that's what that part of the formula is giving us. Suppose I said, what's the probability of all of the tosses becoming 5s? In other words, I toss it 10 times and I get a 5 every time. Well, again, if I plug into the formula, I get a very, 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 very small probability, which should make sense. If I roll a die 10 times, the likelihood I get 10 consecutive 5s should be pretty small. And so here I'm plugging in n equals 10, r equals 10, and p equals 1/6. And notice you get a 0 factorial. Remember, 0 factorial is equal to 1. A second example, suppose we have a case where we have 35% of doctors are females. And so we randomly select a group of 7 doctors. And let's count of those 7 how many are females. So I can think of R as a binomial random variable. I'm going to randomly select 7 doctors, so there's my 7 trials. And each time I select one, there's a 35% chance that doctor is female. So if I wanted the probability of exactly 3 of 7 of those doctors being female, I could plug in n equals 7, r equals 3, and p equals 0.35. So if p is 0.35, that implies q is 65%. 35% of doctors are female, that implies 65% are male. So if I plug that in, I get 2679. Now suppose I said, what's the probability that less than 4 of the 7 doctors are females? So if you think about this, I'm going to have to add up several probabilities. Less than 4 would imply 3 of the 7 are female, or 2 of the 7 are female, or 1 or none of the 7 are females. So I plug those into the formula each individually. So that I'll plug in r equals 3, r equals 2, r equals 1 with my n and p and find those probabilities. Or again, this is a good example where using the probability tables at the end of your book would be helpful. I could go to the table for n equals 7 over to p equals 0.35, and it'll give me the probabilities for each of these values of r, 3, 2, 1, and 0. And I simply add them up.